Hello everyone, this is Doug, and we are going to talk about the malonic ester synthesis and the acetoacetic ester synthesis, which are two specific names of molecules, but really the ideas that we're going to talk about in this video, they're very general ideas, and in fact you've seen most of them already. We're going to introduce one new concept though. So the acetoacetic ester synthesis, right? Acetoacetic just refers to two carbon pieces, right? So it's an acetoacetic. So an acetic ester, right, would be this 2-carbon piece, and then you'd have whatever OR group on there to make it an ester. And then an acetoacetic means you just add another aceto group to that, right? So it's an acetoacetic ester. So that's one of the two molecules that we'll use as a starting point. Now we'll have the acetoacetic ester, but we also have the malonic ester. And the malonic ester, the mal, is just like a 3-carbon piece, and this is just a diester. So you're going to have a diester here. Let me clean that up. You're going to have a diester. What's important about these molecules and why we're talking about them together and in this context is that you'll notice that both of these are beta dicarbonyls. They both are beta dicarbonyl systems, right? If you look at this ester, if you look at this carbon on the ester, that's alpha beta. And if you'd gone the other way around, it would have been beta also. Ditto here, if you take from the point of view of that carbon, you have an alpha and a beta there too. So they're beta dicarbonyls. You have 2 carbonyls is the main point here. Why is that important? Because that is going to give us this doubly alpha hydrogen, right? And I've said in the past that this doubly alpha hydrogen is very acidic. And by very acidic, I mean for a CH bond, right? We're talking pKa's of around 10 to 12 or so, depending on if it's an ester or an aldehyde or what the combination of these carbonyl things are. So they're relatively acidic, right? And so for both of these reactions, they're going to have the same overall formula, where the first thing you're going to do is deprotonate that doubly alpha hydrogen, and then you're going to take that enolate that you just made, and you're going to do some sort of SN2 reaction. This second step here is always an SN2. So first we have acid base, then we're going to have an SN2 reaction with some methyl or primary alkyl halide, right? No secondaries or tertiaries because those tend to do a lot of E2s instead. Then we're going to hydrolyze the ester or whatever this thing is. It might be an amide, it might be a nitrile. I'll show you examples of those later, but this would just be a hydrolysis, right, which we've already talked about. And then lastly, you're going to heat this sucker to decarboxylate your molecule. And to decarboxylate means basically to drive off carbon dioxide. So decarboxylate, you're talking about a carboxyl group, a carboxylic acid. It's going to leave as carbon dioxide. And that's the new part, right? This is the new part for us is a decarboxylation. So let's talk about that. Decarboxylation. For us, we're going to focus mostly on the beta carbonyls, but the idea is that you need to have a carboxylic acid with either a beta hydroxyl group, you need like an OH, or you need to have a beta carbonyl. And like I was saying before in that previous slide, that the malonic ester and the acetoacetic esters, those are beta dicarbonyls. So that's the type of molecule that will be able to decarboxylate. If you have a carboxylic acid and there is an oxo group or a carbonyl that is beta to it, it can decarboxylate and decompose under heat. And I'll show you exactly what that looks like. But to identify these, right, so if I look down at this first one, I have my carboxylic acid, check. And if I look alpha or beta to it, yes, we have a carbonyl. So this is the type of thing that could be decarboxylated because it's a carboxylic acid, and then beta to it is a carbonyl. Perfect. Here we have a carboxylic acid, but this carbonyl is alpha, right? This carbonyl is alpha to that, so this is a no. These do not decarboxylate nearly as easily. They can under other conditions, but this is not what we're talking about for this material. Carboxylic acid over here looks upside down, but it doesn't matter. It's got a carbonyl beta to it, so yes, that is the type of thing that we can decarboxylate under heat. And then you probably are already ahead of me. Yes, I have a carboxylic acid, but this is alpha, beta, gamma. That's too far away, not going to decarboxylate very easily. So we're looking for these beta dicarbonyl systems, and you got to have at least one carboxylic acid. So how does this happen, right? Let's look at the mechanism. I'm going to draw this sucker out so that I can show you all the lone pairs and all that good stuff. And I'm also going to take this carboxylic acid and I'm just going to turn it a little bit. I'm just basically twisting, right, this single bond right here. I'm just doing a little twist right there so that I can get this to look the way I want it to show you the mechanism. All right, so it's the same molecule, right? I just twisted a bond. The reason why you need a beta carbonyl here is because it participates in this mechanism. Because what happens here is that the lone pairs from this carbonyl can grab this hydrogen, right, this acidic hydrogen from the carboxylic acid. Those electrons will then drop down, right, because hydrogen can't have two bonds. It can only have one bond. So if you protonate that carbonyl on the left there, the electrons are going to drop down here, but this carbon can't have 5 bonds, so these electrons have to kick out over to there to give you an alkene. And so this all happens at once, and it all happens if you heat it, right? This doesn't just happen if it's just sitting around at room temperature or cold. You heat this up, and then it will bubble away. And that's going to give you, if you follow all of your electrons, that's attached to that H. That's now double bonded to that methyl. And then what I've done, I'm just going to leave this, it's going to look kind of funky at first, and I'll fix it. But if I just follow exactly where everything was, then I get these two things, right? But we know that this is carbon dioxide, right? This is C double bond L. I'll straighten it out because it should be linear, right? So this is our carboxylic acid, or it's not our carboxylic acid, our carbon dioxide, CO2, right? That's going to bubble away. So this is an irreversible reaction. It's not like the CO2 is going to add back on. And then if you remember, right, this is an enol. And we said to never just stop at the enol, you have to tautomerize. And so then you tautomerize back. Right, tautomerize back to give you that carbonyl back. And so overall, functionally, what looks like happened is that you find wherever your carboxylic acid is, and you basically just erased it. Gone, right? That's what's going to give you that product over there. Now, it's not that the whole thing is gone because that H took the place in that alpha spot. So the H stays more or less, but it's just a carbon and 2 oxygens go away. It's carbon dioxide. And that's the mechanism. It's a one-step electrocyclic reaction, and then you have a tautomerization. So let's look at a couple of examples. Like I was saying here, you're basically just going to erase a carboxylic acid. The other thing stays. So if I want to just look at this one, all I have to do is be like, oh, well, carboxylic acid gone, and then I draw my product, right? And this is the same one that we just did, if it looks familiar. But I'm literally just going to redraw this molecule, not really change anything about it, except that now I have CO2, and where that carboxylic acid is, it's gone. It's replaced by a hydrogen, right? There was a hydrogen here. That's still there. And then this hydrogen that was on the carboxylic acid is now there also, right? Because if you look back at the previous slide, that's the one that gets picked up by the carbonyl and then tautomerizes back. So it's effectively just gone. So we just redraw it without those hydrogens. And that's your product. And I can do the same thing for the two below here, right? Here I have a dicarboxylic acid. It's not going to matter which one I pluck off. It's going to look the same either way. I'll pick the left one just to look a little different. That whole thing's going to be gone, and then my product is going to look like this. Come on. Just going to look like that, right? Just redraw it. You've got some, you've got a carboxylic acid now, and a carbon dioxide has separated from it. So you decarboxylated it. And then don't be afraid if these don't look like they're drawn out, right? That's a carboxylic acid. It's a carbon with double bonded to an O and an OH. And so this also will disappear. Disappears from your structure, and now you have carbon dioxide, right? So that decarboxylation step's the new piece for you. And you have to have a carboxylic acid, have to have a carbonyl that's beta to it. So let's put that in the overall context of these acetoacetic ester and malonic ester syntheses. Right, again, here's the 4 steps, and we'll just go through them together. Again, we have this really, really acidic set of hydrogens here, right? Because it's alpha to the left-hand carbonyl and alpha from the right-hand carbonyl. So you can choose like so many different kinds of bases here. Oftentimes, if this is an ethyl, let me do this. It's kind of like the Claisen, where it's probably not a bad idea. If this is an ethyl ester, usually we use an ethyl alkoxide, right? Ethoxide in this case. So I'm just going to redraw that over here. Here's my OET. The idea is that I've got hydrogens here. We're going to pluck off one. And so pluck off one hydrogen. We're going to form that enolate. And then we have resonance structures where we can go into either of those carbonyls. And the last one. All right, which is why this is so acidic, is because it's got so many resonance structures. And now, but the idea here, right, is again, we have an enolate, which is nucleophilic. That was step one. Step two, apparently, is that we add, in this case, an ethyl bromide. So that means our enolate is just going to attack, right, do that backside attack. We said that was an SN2 type reaction here. I use a bromide. You could use, it could be a tosylate or a triflate or something like that. It doesn't matter. And so now we've added an ethyl piece here. Now step three is just going to do a hydrolysis, right? So step three, we're going to do a hydrolysis. Remember, we had the base mediated or the acid catalyzed one. I chose the acid catalyzed one here just to pick one. Since this is an ester, I'm going to have to heat it up anyways, but that's actually going to help me decarboxylate also. But I'm going to draw the carboxylic acid first. All right, so you turn it into the carboxylic acid. And because there's heat around, that means that also we're going to decarboxylate, right? So that means that I'm going to lose this carboxylic acid. It's gone, it's going. And so I'm going to end up with carbon dioxide and this piece, a 2-carbon piece hanging off there, right, from what was the alpha carbon. And so this would be my product. Right, I've managed to alkylate in that alpha spot, and I drove away carbon dioxide, so I got rid of some carbons. And that would be an example of an acetoacetic ester synthesis. Main purpose, it's good at making CC bonds. Make CC bonds at the alpha spot. So how does this compare to the malonic? The malonic is going to be just about the same thing, right? Almost the exact same thing. I'm just going to start with the malonic ester, the ethyl malonic ester. First step is the same. I'm just going to generate that enolate. Right, plus it has resonance structures. I'm not going to draw them, but right, plus the 2 resonance structures. So that's your step one. Step two is that you're going to add this benzyl bromide. So again, just an SN2 attack. Go do your backside attack on that primary alkyl bromide. That'd give me that. And then again, step three, I'm going to do the hydrolysis. And so the idea is that as soon as you hydrolyze these back to carboxylic acids, I'll go ahead and I'll draw that for us. So I have the 2 carboxylic acids. Since there is heat around, it's gonna decarboxylate, make carbon dioxide. And again, in this case, I have 2 carboxylic acids. It doesn't matter which one you cleave off, if it's the left or the right. Let's just choose the right-hand side to give us our product. And there we go. The question I get a lot from students is, well, since they're both carboxylic acids, do they both decarboxylate? And the answer is no, because right here at the product part, you'd no longer have that beta dicarbonyl system, right? You only have 1 carboxylic acid. You don't have that beta carbonyl to help it decarboxylate. You need that there. So even if you have 2 carboxylic acids like you do on the right-hand side, you have this dicarboxylic acid, only one goes. Just only one goes. Pick which one, it's fine. So here's quite a few examples. This is a good place for you to probably pause, see if you can do these two. Yeah, why don't you pause, see if you can do these two, see if you can see what's going on here. I'll give you a sec. All right, so if we do go through this here, right? So for this first one, looks like we add ourselves a base, check. So step 1, and I'll just skip to step 2 also. Looks like I'm adding this ethyl piece. I know that I'm gonna get this. Or I've added an ethyl there. But if you notice, this has more steps. It has step 3 and 4, because I still have 1 alpha hydrogen here. And so if I add another base now afterwards, I can generate a new enolate, right? A second one. And I can add a second, group here. In this case, just a methyl. Right, so I was able to add 2 alkyl groups. I have 2 alpha hydrogens. There's no reason why you can't. It does tend to get a little crowded and things will slow down a little, but you can do it. And then in the last step, I do the hydrolysis and heat it up. And I know that this side is a ketone, so that's not going to hydrolyze to a carboxylic acid. The right-hand side is an ester that will hydrolyze to the carboxylic acid. And so I can just get rid of, well, I'll draw it out. I was going to say I'll just get rid of the ester, but I might as well draw it out because I don't want to confuse anyone at the beginning here. Right, so it's this ester that's going to, or the ester, what was the ester, now the carboxylic acid is what goes away to give us our product, which will then look like this. That would be my product, right? Where, so if I look back here at this alpha carbon here, right? I added a methyl and I added an ethyl. So that's why I see a methyl here and an ethyl here. Methyl from this and an ethyl from that. That'd be my product. Now this one down here, I switched things up just slightly. I used NaH, which is as a strong base. It's not very nucleophilic, so I don't really have to worry about it doing dish eliminations or anything like that. But again, step 1 and 2 here, looks like I just add on this piece. So I have an alkene at the end, and then so 1, 2, 3, 4 carbons, alkene at the end. So it looks like I'll have this 1, 2, 3, 4. Looks like I added that. And then step 3 and 4, looks like I'm doing that. That's a hydrolysis, the base-mediated hydrolysis. So I'll go ahead and get rid of the esters and bring my carboxylic acids back. And then heat, right? Then if I heat it up, we will get rid of one of these. It doesn't matter which one of these. Which should give me something like that. And let me double check my work. Here's that alpha carbon. I needed to add this 1, 2, 3, 4 carbon piece. 1, 2, 3, 4 carbon piece. Looks like I'm good. This would be my product. And I'll show you a couple more here. I don't want to drag this video out too long. But so the top one was the acetoacetic ester synthesis, and the bottom was the malonic ester synthesis, but they don't have to be those two molecules for this type of chemistry to work. Right, like let's look at these. In the top one, I have an amide, and in the bottom one, I have a nitrile. Neither of these are acetoacetic ester or malonic ester. They're different types of molecules. However, they're very, very, very similar in that they both have these doubly alpha set of hydrogens in the middle, where you have a much lower pKa than you would with other types of CHs. And both of them have two resonance structures, right? You can go to two resonance structures for the carbonyls for the top one, or you can have a resonance structure in the carbonyl and then into the nitrile, right, onto the nitrogen in the second one. And so it's the same type of chemistry, right? It's like the same exact thing. So in the first one, I'm just going to add a base. It kind of doesn't matter what base. That's the doubly alpha hydrogens are the most acidic ones, so they're going to be the ones that go. And then I'm adding this whole tosyl piece. So after steps 1 and 2 here, still going to have my dimethyl amide here. Then I have a carbon 1, 2, 3, 4, 1, 2, 3, 4, and then that has a split there. And then it looks like I have a hydrolysis for my step 3 with heat. Doesn't change the ketone, but will hydrolyze the amide to give me that piece. And then again, like always, since I have a carboxylic acid and it has a beta carbonyl, that carboxylic acid's going to give me my product. And you could straighten this out if you want, or whatever you want to do, but that would be your product, right? Plus CO2. So it doesn't have to be those two molecules. It can be anything that has that beta carbonyl, or in this case nitrile, right? This really stable enolate. This is just enolate chemistry here. So same thing for this one, right? I've got the hydrogen in the middle. If I go step 1, I'm going to get an enolate that is resonance stabilized. And I'll draw the resonance structures out just to make sure we're on the same page here. Right, where you have the O- and the C triple bond N. Right, there's a C there. And then the other resonance structure. Right, so you have these resonance structures. So again, that doubly alpha hydrogen is much more acidic than a normal CH. It's easy to take off with hydroxide. And I'm going to do kind of two fancy things here, right? So step 2, I'm going to add this big old long sucker. It looks like it's 1, 2, 3, 4 carbons. So I'm going to have this 1, 2, 3, 4, and then there's an OH coming off, right? 1, 2, 3, 4. And then step 3 is using SOCl2, which I know turns alcohols or OH groups into chlorides. So that means that this is now a chloride. Step 4 is adding base again, and I do have a second alpha hydrogen here, so that sucker can be pulled off. One, two, three, four. 1, 2, 3, 4. Cl. And what's kind of cool about this is that this enolate, this negative, can then attack that chlorine, which is doing an intramolecular reaction, to give us a cyclic compound. So this will be 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons. So I end up making this 5-membered ring. And then the last step here, right, is your hydrolysis reaction, which eventually is going to turn your nitrile back into a carboxylic acid, and that will then leave. So step 5 actually here. To give us this molecule. So there's lots of fun things that you can do with these. They're all pretty similar. Again, you just need a beta dicarbonyl system. So you have those really acidic hydrogens, so you can pluck them off, use the enolate to act as a nucleophile to attack an alkyl halide of some kind of sort, do a hydrolysis, decarboxylate it, boom, you're done. I want to give you one more last example, which is you coming up with a reagent. So take a look at this, right? I want to know what reagents do you need in order to do this. Sorry, I accidentally just turned on some rock music. Perfect. What reagents do you need to add in order to turn this molecule, the first molecule into the second molecule? And you may have noticed that on the other ones that I was doing, I was looking at this doubly alpha carbon and asking myself, well, did I get the right stuff on the right place? Because this to me, right, definitely looks like carbon 1 and 2. It's probably carbon 1 and 2. And it looks like I added that and that. That's as much of a hint as I'm going to give you. Pause. Try this yourself. Okay. So one way, and there's many ways you could have done this, but one way you could have done it was to say, okay, well, step 1, I'm going to add isopropoxide, or you could use like NaH or LDA or something that's not going to interfere with the ester. That's going to make your enolate. And then step 2, you pick one of these to put on first. Not going to really matter too much which one. For us at this point, let's say I want to put on the cyclopentyl thing first. And maybe I'll put an OTS on it, a tosylate on it. So that would get that first one on there. Then I can add isopropoxide again. And then I'll add my 1, 2, 3, 4 carbons. So 1, 2, 3, 4. And then maybe I'll use bromine on this one to get on that other piece. And then my last step, I need to hydrolyze that ester away and add some heat so I can do the decarboxylation. And that should give me that product. Again, your leaving groups might be different. Your bases might be different. You could have used the base mediated hydrolysis at the end, but something along those lines would have been good. So I hope you have a little better sense of the acetoacetic ester synthesis and the malonic ester synthesis. The chemistries are all things that we've kind of seen before. The only new thing is the decarboxylation. So study up. Good luck.